Let's take a look at high order finite difference derivatives, which we're going to use on numerical calculations. For instance, the first derivative to second order accuracy is given by this expression. To fourth order, this is the expression. To sixth order, this is a numerical derivative. You may wonder where these coefficients are coming from. So the table below shows the coefficients, which are the weights, these weights that are given to each point when computing a derivative to desired accuracy. Here I said that this is the first derivative to sixth order accuracy. So that means here, first derivative to sixth order accuracy, and here you have the coefficients. So the point -3 in the stencil has a coefficient -1/60, which is what you see here. The point -2 has coefficient 3/20, that's what you see here, 9/60. The point -1, 45/60, that's -3/4. 0 is a coefficient of the center point, and the same coefficients flipped sign on the other side for the points 1, 2, and 3. So this is how you use this table. Thus, we will draw from this table to compute first and second derivatives, mostly, which are the ones that we use the most in numerical hydrodynamics. But how are these coefficients determined? Well, the coefficients, they come from Taylor expansion. Suppose that we want to compute the f dx to second order accuracy. So let's use a 3-point stencil. Then using a 3-point stencil, we have the central point, the point -1, and the point +1. Here as x minus h and x plus h, where that means that the central point is x and delta x is equal to h. So according to the table above, we should have for the second order accurate first derivative, the coefficients should be -half, 0, and half. So let us prove this. Well, let's Taylor expand around x. Let's take the first term here, f x minus h. So the Taylor expansion around x would give us the value at x plus the first derivative at x times x minus h around x, so that's just minus h. And the second derivative, h²/2. fx, that is at the point, so that's just the function itself. And at the point x plus h, you do the same thing, the Taylor expansion around the point x, with the first derivative, the second derivative, the higher order derivatives, multiplied by the powers of the deviation. H here for the first order, h²/2 for the second order. So there you go. You have here the Taylor expansions to second order of the 3 terms. If you sum the 3 terms, you must have the first derivative. So summing them all, this is what you get. So this is the sum of the 3 terms, and grouped now in the terms that are multiplying the function f of x, the terms that are multiplying the first derivative, and the terms that are multiplying the second derivative. And now we equate the left-hand side, which is only the first derivative, to the right-hand side, which has the function. So this coefficient must be 0. The coefficients of the second derivative must also be 0. And this has to be 1. So since only the first derivative should survive in the right-hand side, this leads to these conditions. This is equal to 0, a plus b plus c is equal to 0, a minus c is equal to 1, and a plus c is equal to 0. So in matrix form, this is the equation, which we can invert here, as you see. This is the matrix. And so for the coefficients, -half, 0, half. Indeed, -half, 0, half is expected. So let's do another example. Let's find the fourth derivative with a 5-point stencil. So the fourth derivative with 5 points. The central point, -1, -2, +1, and +2. Then the coefficients here would be a, b, c, d, and e. If we expand the terms to fourth order accuracy, this is what you get here for a again. So you get the function at the point x minus 2h. That's the function at the center point, plus the first derivative times the variation, which is -2h. Second derivative, 2h²/2. Third derivative, -2h³/6. Fourth derivative, 2h4/4 factorial, which is 24. Do the same thing for the other terms, b, c, d, and e. And this is what you get. Now, doing the same thing that we did before, grouping together the terms that are of the same order in the derivative, this is what you get. Sum here, a, b, c, and d, and e, which are multiplying the f of x. The terms that are multiplying the first derivative are minus 2a minus b, d, and 2e. And the second derivative, you have 2h squared, have 1 in b. You have 2h squared in a, you have 1 in b, 1 in d, and 2h squared in e. For the third derivative, minus 2h cubed, minus h cubed, and 2h cubed. So you can already see a pattern. It's the stencil, minus 2, minus 1, 1, and 2, to the power of the order of the derivative. Here on the third order derivative, the power is 3. On the fourth order derivative, the power is 4, and so on. So this is the system that we have in the end. We cast this in matrix form and invert the matrix. There we have the coefficients, 1, minus 4, 6, minus 4, and 1. And here are the numbers. The fourth order derivative to second order accuracy, that's the 5-point stencil. You have coefficients 1, minus 4, 6, minus 4, and 1. Precisely what we found here. So let's see what we did here. Let's see if we find a general recurrency relationship. What we had here was that for every order in the derivative, say for the third order or the fourth order, the equation that we had was the position in the stencil to the power of the order and given either 0 or the factorial of the order. It means that in general, this is a recurrency relationship. You have here the position of the stencil, the order of the derivative, so from 0 to 4, and that's going to give you either 0 or the factorial of the order. That's what the delta is doing here. If the order is 4, this delta is going to be 1. Otherwise, it's going to be 0. We can distill from this the general formula. So the bases are the set of stencil positions, call it S, being minus 2, 1, 0, 1, and 2. And then the coefficient C, which we have been calling A, B, C, D, E, are set by this recurrency relation. So we have here the positions of the stencil, S to the power of N, and the coefficients C, I, which goes from A to E. So that's the sum here, and this sum goes from 0 to n. N is the size of the stencil. And on the right-hand side, you have d here, that's the order of the derivative, factorial. Where n is the size of the stencil, and d is the order of the derivative. So let's apply this formula. Let us calculate to this formula the second derivative to fourth order accuracy with a 5-point stencil. So let's go to the table, second derivative to fourth order accuracy. So second derivative, fourth order accuracy, we need indeed 5 points in the stencil. And these are the coefficients that we should find, minus 1 over 12, 4/3, and minus 5/2. Applying the recurrency formula, the matrix is the same that we found before since the stencil is of the same size, it's 5 points. Now, the only difference is that now we are wanting to calculate the second derivative. So the order is d equal to, all the terms in the right-hand side are going to be 0, except for 0, 1, and 2, the second derivative, which is going to be given by 2. So let's invert this, and this is what we find. And indeed, in rational numbers, these are minus 1 over 12. This is 4/3. This is minus 5/2. And again here, 4/3 and minus 1 over 12, exactly as stated in the table above.